In this video, we will look at how a neural network solves an image recognition problem. The tutorial is based on a MATLAB example. The MATLAB example we will use is for digit recognition. MATLAB conveniently sets up the network for us and has the required dataset stored. Although we are using MATLAB here, you can use any language to build your neural network, Python being the most commonly used for this task. I do not wish you to learn MATLAB programming for this tutorial, only the procedure needed on how to set up a network and apply it to a problem. This example is similar to our dot and one recognition example in the previous video. However, this time we will try to recognize handwritten digits. The size of each image is 28 pixels by 28 pixels. The image is grayscale, and so each pixel can take a value between 0 and 255 inclusive, as compared to our simpler 0 or 1 in the last example. If we consider every possible combination of variations of this image, this gives us over 200,000 combinations. If you could write an if statement in 10 seconds, this would take you 23 days to write the equivalent program. To further emphasize the point, GoogleNet is a well-known image recognition network programmed to recognize 100 objects from its 22-layer network. With an input size of 224 by 224 for an RGB image, this gives us over 800 billion input combinations. Our if statement equivalent program would take 267,000 years to write. We need to train the network, although practically we cannot use all 200,000 variations of the dataset. For this example, there are a total of 10,000 data corresponding to 1,000 examples of each digit. The link for the MATLAB example is shown here. I've slightly modified the code to include examining the network once it has been trained, so go onto Canvas and use the code given for today's session. The code will work as given. You can just copy and paste it into MATLAB. We will discuss the structure of this neural network in the next video. However, for now, there are a few lines of this code that you should pay particular attention to. As this is supervised training, we need to tell the network what output corresponds to the different inputs. One option to do this is to create an image data store, here labeled as variable IMDS. The data is stored in a set of folders. The digit dataset path parameter stores the link for these folders. The option of label source and folder names tells MATLAB that each set of data is stored in a separate folder, and the correct output for that data is the folder name it is stored in. Thus, for example, all images of digit 0 are stored in a folder called 0. You train a network using data, and this network, if trained correctly, should perform well in recognizing this data. For example, if you train with an image of 2, then you would expect the neural network to recognize this image of 2. However, what if someone else writes the number 2? Will the neural network recognize this, as it has not been specifically trained on this data? What validation does is to split the data set into data used for training and data used to check how well the neural network performs, known as validation. The network does not use this validation data during training, so once the network is trained, this validation data is entered into the network as new data. This allows us to see if the network works on this unseen data as good as it does on the training data. The MATLAB command shown here automatically splits the available data into data for training and data for validation. We will not explore the mathematics on how a network trains itself, but we must understand the process so we can set appropriate training parameters. Imagine we have a neural network with one input weight and one bias. We thus have two values we need to determine. For a given combination of these two values, the network may perform poorly, giving a large error, or perform well, giving a low error. If we consider every possible combination of values, we can plot this out as a surface where height corresponds to error. We need to find the lowest possible point. The plot may look something like this. We can see that some combinations give a large error, the higher points, and some give a low error, the lower points. Only one point on this plot gives the best solution, although there are other points with give good low error solutions. Ideally, we would like to find the lowest point. In this simple example, we can clearly see where the lowest point is. However, remember that this example is extremely oversimplified. In our recognize a dot example, we had 11 weights and biases to determine, so we would have an 11-dimensional surface to consider. For GoogleNet, we are talking a multi-million dimensional surface. So in reality, it is unfeasible to plot out this surface to find the minimum value. We need a technique to find it. What we will do is try some points at random and work from there. On our surface, we will pick a point at random, say this point here. It would be a good idea to move in the direction of steepest downward gradient, so from our current position we will move in this direction. In our training options, we will thus pick the stochastic gradient descent option, which will move our first estimate down the steepest slope. Our next option is learning rate. This essentially sets how far we move down the slope before we recalculate the gradient. If it is too small, the training will take a long time and the solution may get trapped in a local minimum, i.e. a slight dip in the surface. If it is too large, then we may shoot past the solution we are looking for. Usually the training rate is set at some medium value. Once a training step is completed, the gradient is evaluated again, and the next direction to try is decided. If you imagine a marble rolling down this surface, it would not instantly change direction at the next training step. Its momentum would keep it moving to some extent in the current direction, and it would start to roll more towards the new steepest gradient. This is what the stochastic gradient descent with momentum solver is doing. We can also set the learning rate to change automatically to smaller values as the solution is approached. After several steps of doing this, we should find the solution. In this case, we have found a good solution, but not the best. This is because we started in the wrong place, although we do not know where is the right place to start. What we can do is repeat the training, but start from another random place. Hopefully this time we will find the best solution. This is what the epoch setting is. How many times do we want to redo the training to make sure we have found the best solution? We can assess how many epochs we need by watching the training process. This is shown in the next video. There are lots more options for training, but these are the main three we need to concentrate on. The train network command in MATLAB performs the training step, and in this case saves it to the variable named net. This command needs a link to where the data is stored, the geometry of the network and the training options. The last few lines of code gives us a measure of how well the network performs. This uses the validation data to check the results. The confusion matrix plot is useful, as we can see where the network performs well and where it performs poorly. In this case, it generally performs well for all cases, with 100% accuracy for the obvious one digit, but does sometimes struggle between an 8 and a 3. Now it is trained and verified, we want to use this for our application of recognizing written digits. Let us see if it can recognize my handwriting. The input image size needs to be 28 by 28 by 1. We will create an image of this size. Note that we could create a larger image, and then use the MATLAB image resizing command to scale down this image. What I will do is open Paint, and set an image size of 28 pixels by 28 pixels. I'll then draw in a number. As our training data is white on black, we need this for our image also. Once completed, I've saved out the image to my MATLAB working directory. My writing of the number 3 is not perfect, and is different each time I do this. Thus the image on this slide is slightly different to the video. However, the point of AI is to recognize any drawn 3, not just a specific example, so if the network is good, then it should still work. The process of saving an image in Paint is to save it as an RGB image, so the image will be saved with a size of 28 by 28 by 3. Therefore, my first line of MATLAB code changes this RGB image to a grayscale image. This is done by taking 1/3 of each of the red, green, and blue components. If we now put the image through our network, using the MATLAB classify command, it should tell us that the number I have written is the number 3. Here's the program code from Canvas. On running it, the network will be trained. I have a dedicated GPU on my laptop, so the training will be relatively quick. Once trained, if I paste in the code to load my image and recognize it, the network correctly categorizes it as a 3 in this case. In the next video, we will repeat this example, but look at building our own network up from the start, thereby seeing what layers are needed.